Does this work?
I'm not sure. Is it the power switch?
Awesome. Thank you.
So welcome back, everyone. Our next presenter is Stefan Heule from Google. He's been working on networking there for a while. Did a PhD at Stanford before joining Google. And today he's going to be talking about using automated techniques to generate test cases for P4 programs. Thanks.
Thank you for the introduction. All right, I want to start my talk with a little bit of background. So traditionally for fully programmable switches, the way you use P4 is you write your P4 program and you come up with whatever you want, and it's really flexible. And then the P4 compiler will take that program and compile it to whatever programmable switch we have. And these programmable switches might look like something like what I'm showing on a slide, where you have a fully programmable parser and then a bunch of sort of general purpose logic that can implement the match action pipeline that your P4 program has. And this is great, and basically the P4 program fully determines what the hardware is going to do. Now, at Google and in many places, there's still a lot of fixed function switches. And so if you want to use P4 in a setting like that, then the switch is going to look something like what I have on the slide here, where you have a fixed parser and then a relatively fixed pipeline. Maybe there's some L3 and L2 routing, there's some access control lists, and so on. And if you want to use P4 in a setting like this, then one thing that you might do is you basically use P4 to describe exactly what this pipeline does. So you model the hardware in P4, and basically the hardware determines exactly what the P4 program is going to look like. And if you think about it, these are really two ends of the spectrum, where on the one side you have the P4 program fully determining what the hardware does, and the other side you have the hardware determining what your P4 program can look like. And when we started looking at P4 at Google, what we decided is to go with sort of an approach in the middle. We still have a lot of fixed function switches, so the kind of P4 programs we can write are obviously going to be limited by what the hardware provides. But we don't just want to fully describe the hardware that we have, but instead we want to model the use cases that we actually have at Google, and not describe, for instance, tables that we're not going to use. So in certain roles of our switches, there's basically no L2 routing, and so there's no need for our P4 programs to mention L2 routing at all, even though the switch technically has the capability of doing that. Similarly, our tables will only mention the match keys that we're actually using, and maybe more importantly, the tables that we have in our P4 program are really logical tables that have sort of a semantic meaning of what this table is meant to do in terms of forwarding behavior. And it doesn't necessarily, for instance, use the name that the hardware that implements this table actually does. And so we can have a bunch of abstraction that makes it much easier and nicer to work with the P4 program and the sort of northbound interfaces that you get from that. And in doing so, we found that it's really nice to have this very clear contract as part of the P4 program that determines or that specifies what the desired switch behavior is. This really allows us to operate a large heterogeneous fleet where we have many generations of different kinds of switches. It allows us to automatically generate the switch config, at least in part. So if you have a fully programmable switch, basically the P4 program will determine the entire switch config, and you can just use the P4 compiler to generate basically the entire switch configuration. But even for fixed function switches, there's going to be some aspects that need configuration, and for those we can still take the P4 program and basically automatically generate that. So in both cases we sort of get a win. And then maybe most importantly, this really allows us to do automated switch validation, where if we get a switch that is supposed to implement our P4 program, namely the desired forwarding behavior, we can use the P4 program and validate it against that switch. And that's largely what my talk is going to be about. So let's break that down a little bit. We want this approach to be automated. And what we mean by that is we want the test inputs to be automatically generated either from production data or by analyzing the P4 program, rather than having to write these test inputs manually. We are doing switch validation, so we're looking at a single switch or a single switch chip, not an entire network. Obviously, if you want to build a network, you need to also look at the whole network and verify that. While that's important, obviously you're not going to succeed at that if your switch is not doing the right thing. So we're going to start with just a switch. And then we're doing validation, which means we want to take the outputs and make sure the switch is actually doing the right thing. And again, we want this to be automated. And so one of the major routes that we've taken is to use the P4 program simulation to basically have a reference of what the real output is supposed to be. All right, so what do we actually test? In the middle, we have our P4 switch here. And there's sort of two main interfaces that we want to test and validate here. On the one hand, we have the control plane interface that is controlling the switch through P4 runtime, where we install table entries and group entries and so on. And then on the other side, we have the data plane the data plane where we actually send and receive packets. And we want to make sure that both of these interfaces are working correctly. So on the control plane side of things, the first thing we do is we replay production table entries. And this is basically making sure that the switch can handle sort of our current use cases and the ways we currently use the switch. And while this is certainly important and useful, this doesn't cover anything beyond that. So it doesn't cover anything in terms of future use cases that might come down in the future. And it also doesn't help us make sure that the switch is actually reliable in case of something goes wrong in the control plane or what have you. And so to cover those kinds of scenarios, we also have a fuzzer that basically generates random table entries and inserts those into the switch and make sure those are handled correctly. And then on the data plane side, we have something that we call automated test packet generation. And I'll talk a lot more about how that exactly works in a few slides. And then there's also a bunch of other interfaces and sort of features that the switch has that we want to make sure are working correctly. Things like counters or meters, or that the switch is doing the load balancing correctly using hashing and so on. All right, so let's start with control plane fuzzing. The intuition behind fuzzing is essentially you want to come up with random inputs and send them to your system under test and make sure that the system under test is behaving correctly. But one main challenge with fuzzing is usually that you need those inputs to be somewhat well-formed, because if they're completely ill-formed, then your system under test is usually just going to reject them very early on, and you're not really going to test anything interesting and deep sort of inside the implementation of your system under test. And so for our scenario here, where we're trying to test switches, if you send invalid table entries, the switch is just going to reject them and saying this is invalid, and you're never actually testing sort of the implementation where like the hardware is actually being programmed. Luckily, with P4 and P4 runtime, the API makes it very easy to generate these well-formed inputs. And so what we do is, most of the time we generate well-formed inputs, and every now and then we throw in some ill-formed ones just to make sure that the switch is rejecting those correctly. And then once we have all of these sort of insertion and deletion requests, we can send them to the switch, and the switch will handle them and return the status. And then the second task is to make sure that those are actually handled correctly. And again, the P4 runtime protocol makes it pretty clear what the switch needs to do. So for instance, if you have a well-formed entry, then the switch is only allowed to do three things. Either the entry already exists in the switch, in which case it must reject it as already exists, or the switch is out of resources for the particular table that you're talking about, in which case the switch will say so. And in all other cases, the switch must accept the entry and install it in the hardware. And so this is pretty nice, because both on the input generation side, the P4 makes it pretty easy to do that well as on validating whether the switch is doing the right thing. A second thing we can do with our fuzzer is, we know from previous experience that when you come close to sort of the table limits, the switch's implementation are doing a lot of sort of tricky behavior where they like rearrange things in the table and so on. And there's a lot of bugs lurking there. And so we tune our fuzzer to basically generate more insertion requests than deletion requests. And so as you run the fuzzer over time, the tables basically start filling up until we hit the resource limit, in which case they start sort of hovering around that resource limit. And this has really helped us make sure that the reliability of the switch is working correctly, even in the face of the tables almost being full. All right, so that's what we do on the control plane side of things. And I'm now going to move on to the data plane. And the setup there looks as follows. We have our P4 switch, and we also have this P4 simulator called BMV2. And it's open source that we're using. And the first thing is we're going to take a bunch of table entries and install them on the switch. These can be any kind of table entries that you're interested in. Could be production data, or it could be the fast table entries that we've just talked about. And then we're going to take packets, and we actually forward them through the P4 switch that we're trying to test, and we get a set of forwarded actual output packets. We do the same thing for the simulator, where we get a set of expected packets, and now we can just compare. Basically, this is doing differential testing, and we can verify that they're matching. And now, obviously, the interesting question is, how do you come up with these input packets? What kind of packet should you send? And the intuition is, obviously, you want to make these packets cover the entire sort of forwarding behavior that your switch has. Ideally, you would send just any possible packet, but clearly there's too many, so we can't send all of them. So you need to be a little bit more strategic. And so the intuition that we have is basically the table entries determine what the forwarding behavior is of the switch. So if you can generate a packet for every table entry on the switch, then that gives us a lot of coverage. And so I want to talk a little bit about how we actually do that. Like, how do you generate a packet to hit a particular table entry in all of these tables on the switch? So in this example, I have a switch that has an IPv4 longest prefix matching table. And I picked one particular entry that we want to hit. So it's this /16 here, starts with 10.152. And so if you want to have a packet that actually hits this flow, or hits this table entry, clearly, at the very least, it needs to have an IP, a destination IP address that starts with this 10.152. And in addition, it also needs to have the VRF42. And I'll talk a little bit more about what the VRF actually is. But that's actually not quite enough. What we also need to do is, since this is the longest prefix matching table, we need to make sure if there's any other table entries installed in this table that have a longer prefix, those will take higher precedence, and so we need to avoid hitting those. So if we sort of amend the formula that I'm building down here, we also need to make sure that we don't accidentally hit these longer prefixes. So here, the one with the start of 10.152.8. And we need to do this for any other table entries that might overlap. Okay, so far so good. We now have the right destination IP. And then there's also this VRF thing that's not actually a field on the packet, but instead this is assigned earlier in the pipeline in the VRF classifier pipeline, VRF classifier table. Basically, that table matches on a number of fields, and then its action is to set this VRF. And clearly, if we want to have VRF42, we need to hit one of the entries in this earlier table that actually sets that VRF. And so just like before, we do basically the same thing. We say, well, we need to actually hit an entry where we do that. So maybe we take the ETH type of 0800, and we want to have port number 4. And then similarly, just to before, we need to make sure we avoid anything that might have higher priority in this VRF classifier table, just like I've outlined down here. And now we essentially have this logical formula that tells us whether a packet is going to hit this particular table entry or not. And there's these off-the-shelf solvers called SAT solvers that are extremely good at basically solving exactly this kind of formula. And they will tell us, is there a packet that actually is able to hit this particular table entry? And if there is, it will also give us an example of what the packet might look like. Basically, it gives us all of the fields that the packet has, including destination IP and so on. And so what we do is we basically do this for every entry of every table and generate at least one packet for each of them. And then we can send them. We can send all of these packets to the switch and compare with the reference simulator and make sure the switch is forwarding them correctly. Okay. And in our experience, this is actually working really well. And the reason for that is that SAT is really an excellent match for sort of switches and P4 in particular. And if you've done any sort of program verification before, you might know that that's a really hard problem. And in general, if you give sort of a general program to somebody and say, like, prove some property about it, that's a really, really difficult problem. But the reason that this is such a good match for P4 is because in our switches, basically everything is finite. There's no lists, no loops, no recursion. And so SAT solvers are really, really good at those kinds of problems. And so this works remarkably well. And with this, we sort of have this very powerful tool that we can use to ask these complex questions. So in what I've just shown you, the question that we were asking is, what does a packet look like to hit a particular table entry? But you can also ask other questions. You could ask the question of, what does a packet need to look like that gets forwarded on port 4? Or are there any packets that get forwarded on port 4 and they have a specific destination IP? So this is pretty general, much more than what we're using it here for. And we're looking forward to exploring future use cases as well. Another thing that I wanted to mention here is this sort of idea of differential testing where you have the P4 program be your specification, and you can implement it using, or you can simulate that using a simulator like BMV2 and sort of compare against the switch is really powerful. So with this, we can very easily test like all kinds of other aspects of the switch. So for instance, if you want to test whether the counters are incremented correctly by your switch, what you can do is you can basically install a number of table entries on both of these switches, send some traffic through them, and then compare the counters at the end. And actually what we do for testing counters, we use the exact same packets that we just came up with to test the forwarding behavior to also make sure that the counters are incremented correctly. One challenge that we came across, though, was hashing. So these switches, when you have a group with multiple members, you can do sort of load balancing over them using ECMP or WCMP, where you basically give a weight to every member in the group, and they get forwarded according to that weighted distribution using a hash. And a lot of these fixed function switches make it pretty tricky to really know exactly what this hash function is. And so usually you're not able to train or to have your simulator predict exactly what port or what member of the group is being used. And so how we worked around this is essentially we have the simulator predict the set of ports that a packet could get forwarded on. And then we just require that the switch sends the packet out on at least one of those ports. But and that sort of makes sense, but makes the whole testing a little bit more challenging since now there's not a one-to-one correspondence between the two. And then in addition, of course, you need sort of a second test where you actually test whether the load balancing is working correctly. And in particular, what you would do is you send a number of packets to the switch, and you make sure that the distribution is as you would expect, namely according to the weights of your members. All right, so I've just sort of described how we use the P4 program as a specification to validate these switches, and we've been pretty happy with this approach. We have a small number of developers that basically created a pretty extensive set of automated tests that essentially test the entire sort of control plane and data plane interfaces to the switch. And this is definitely not something that would easily be doable if you had to sort of manually write these tests. So we got a lot of leverage out of having the P4 specification be very rigorous and then building automated tools that sort of do the testing automatically for us. And we found a whole number of bugs in sort of the project that we've been using this for. In particular, I think the number is well over 100 at this point. And what's also interesting, we found these bugs in a number of different components. So the first component we found bugs in is the switch software stack. This is sort of expected. Like the outline that I started with is you have a P4 program, that's your specification, and you want to test whether the switch is implementing that correctly. And so, of course, you're going to find problems in your switch software stack. But interestingly, we also found bugs in our SDN controller where the SDN controller was essentially doing the wrong thing. We found bugs in our P4 programs where basically sometimes when you test your switch against the P4 specification and you find a discrepancy between the two, it turns out the switch was actually doing the right thing, but your specification was wrong. And so really you're sort of testing whether the two match, and if they don't, a human sort of has to look at this and decide whether the problem is in the switch or whether your specification is wrong. So we also had a number of times where the P4 program that we wrote was just wrong, and we had to fix that. We found some bugs in the P4 runtime protocol, and we've been working with the P4 runtime working group to get that fixed. And we found a number of bugs in the P4 program simulator, as you might expect. One thing that you might notice is absent on this list is the switch ASIC. So the switch ASIC, we didn't actually find any bugs in that. I think part of the reason for that is the ASIC that we were using is a pretty mature ASIC, so lots of people have played with it and tested it. And also, since it's hardware, people spend a lot of time making sure the hardware is right, because if it's not, it's really, really expensive to fix problems. It's much easier to fix problems in software if you discover them late. And so in conclusion, I think we found it extremely valuable to have P4 be this very rigorous contract of what the switch's behavior is supposed to be. It really enables us to operate this large set of heterogeneous switches. And maybe most importantly, we can do all of this automated switch validation where we very quickly were able to test a sort of a complicated set of APIs and make sure it works correctly, and we found a pretty broad number of bugs. And with that, I'd be happy to take any questions if you have any.
Earlier, when you were talking about the comparison between the P4 simulator and the hardware, and that visual, I guess I'm curious about the control plane bugs that you found and like how you arrived at those bugs, like which set on which side, you know what I mean?
Yeah, so let's see if we can, like this one.
Yeah.
Basically, how did you find, like in this scenario, there's no SDN controller, so why did you find bugs in the SDN controller? Yeah, that's a very good question. So one thing that I haven't shown, especially on this slide, is we also do, but I did mention earlier, we also do replay of production traces against the switch. And essentially, I think that's where most of the bugs in our SDN controller came from, where we were replaying things against the switch, and in particular, against a real switch as well as a simulator, and one of the two was like, that doesn't make a whole lot of sense, what are you sending here? And we were like, yeah, that's actually true, like we should look at where these things are coming from, and it turns out the SDN controller was not doing what we really wanted it to do.
I see. So at no point in like this type of scenario do you have like a true production side, like running like a latest release of the controller and then actually applying those, and then the other side being a control of like, these are exactly the table entries, like that type of comparison?
Yeah, so I can actually say a little bit more about how this works. So at Google, many of you might know, we've been using OpenFlow for a long time. And so in sort of trying to migrate to P4, what we've done is we basically convert OpenFlow to P4 and sort of like just before you go to the switch. And that allows us to sort of transparently switch from OpenFlow to P4 for the switches, but like have all of our SDN apps still use the OpenFlow-based abstractions, so that we don't have to change the entire system at once. And so what we do, we obviously have lots of production flows that are actually used in production, and we just take them, convert them to P4, and then use them for this kind of testing.
Okay, awesome, thank you.
So the VRF that you showed,
yeah.
How did you come up with that? Is that a hash function, or is it something you define? Because it's not very clear on that.
Yeah. Let's see if I can find the slide. So here. Basically, what does VRF stand for? I forget what VRF stands for. Thank you. So the way we use this at Google is basically, this is used to classify traffic in an earlier table, and then we make decisions based on that earlier classification. And so these are just literally numbers that somebody picked. They're not necessarily meaningful. So the fact that this is 42 doesn't really mean anything, except that it links this sort of classification earlier in the switch pipeline to then the later matches where you can also match on this. So basically, you think of this as classifying traffic into a small set of classes.
So just a random number that you.
That's right, and then matching on that.
Yeah. So VRF is basically a way to partition a single LPM table into multiple logical tables, where each logical table is identified by an ID. In this case, 42.
Yeah.
Do you have any plans to share any of your work with the community?
Yeah, that's a great question. We definitely want to. There's always a challenge. Like we've done this sort of like internally, and now we have to like go through the motions of like actually making this accessible and to remove all of the links deep into our infrastructure. We're hoping that at least this information is useful, but we do want to share this more broadly, in particular code that might come with this. I can't really give you any estimated like when this is going to happen, but we want to.
I guess that kind of directly follows, or this kind of directly follows up. So like P4V with the Z3 and test vectors and this, is this going to come together kind of as a holistic test suite sort of deal? Or how do you guys see this flowing together? Yeah, that's also a great question. I think at the moment, it's a bunch of different people doing a bunch of cool things and not necessarily having like an overarching strategy. I think it would be great if these people get together and talk a little bit more. I think P4V in particular is almost a little bit orthogonal, where there you're trying to make sure that the P4 program that you write is correct.
Versus here, we sort of assume that your P4 program is what you want, and we test that the switch is actually doing what the P4 program says it's supposed to do. So some of these are somewhat complementary. But yeah, I think that there should be more collaborations.
So I think you mentioned that you went from, at Google, you went from using the OpenFlow, current OpenFlow implementation and the flows, kind of migrating that into P4. Where do you really see the power of P4 in that process? I mean, I can see the validation part of it, but where do you see P4 really benefited you guys in terms of really creating the next generation SDN?
Yeah, great question. I think the validation, it really is one of the key aspects. But maybe more broadly, it just having a clear interface to the switch, I think has really helped us a lot. I don't know how much you've worked with OpenFlow, but it's very difficult to know when you write sort of, an OpenFlow match action rule to know where exactly does that end up in a hardware. And so there's a lot of things you can write where like it's not even clear whether the hardware can implement this at all. And so P4 is much more structured. And so with that, you can sort of catch a lot of bugs much earlier in sort of the development lifecycle.
Yeah, quick question. Are you testing on Tofino? And if so, how do you deal with the ingress and egress pipeline versus the BMC much simpler pipeline?
Yeah, so right now we haven't tried this on Tofino. There's not really anything stopping us from doing it, except we haven't gotten around to it. I think one thing with doing this on a Tofino is in that at that point you're sort of more testing like whether the compiler is working correctly and like whether the switch is working correctly, and like in most cases you sort of assume that is like as a user of a Tofino switch, I assume you're going to trust that the compiler is working correctly. The reason we find a lot of value here is because we're doing this with a fixed function switch, and so there's a kind of a lot of translation that goes on from programming through P4 runtime and like how you actually program the hardware. But I think it would be interesting to try out.
Other questions?
I just have one more.
Sure. On that line of thinking, I guess, is there any interest, or do you guys see value in like ASIC modeling, or like an ASIC emulation layer to accompany this? In the case of Tofino, like the Tofino ASIC model, and then in other vendors like an ASIC emulation layer. Like, does that register in your thoughts?
Yeah. I guess we've enjoyed staying sort of like relatively abstract with the P4 program, and we found that to be a sort of good abstraction layer between like sort of what the switch is doing at the bottom and like what the SDN is doing at the top. I think if you wanted to work more with that kind of system, you would be more talking about like lower level stuff. But yeah, I don't think we have any concrete plans in that direction, I guess.
I've got a question for you too.
Yeah.
So for a given flow table snapshot, you might have tens of thousands or hundreds of thousands of flows. Mm-hmm. How expensive is it to actually compute these packets?
Yeah, that's a good question. So I don't think I have any numbers for 100,000 flows. I don't think we have tried that yet. I think the sort of set of flows that we've tried this with is maybe on the order of like 3,000-4,000 flows. And there, it works reasonably fast. Generated packet for all of those is maybe on the order of like a minute or two, or something like that. I don't quote me on the exact numbers.
On Google's cloud or on a single server?
No, on a single machine. So okay, let me say a few things. Obviously, you're not generating this traffic at light run rate, right? Like I'm talking about like generating 1,000 packets in like a couple of minutes or something like that. So it's not super fast in sort of like switch terms. But since we believe that set of 1,000 packets is really giving you enough coverage to test the entire switch, that's really fast, right? Basically, you can test the entire switch in like a couple of minutes. And yeah, it's not Google Cloud scale, so just a single server.
And to follow up on your hashing question, so are you actually using knowledge of the hash function as defined in your P4 program to add entropy in the wildcard sections in your stat solver, or are you generating arbitrary entropy and just hoping that statistically you get a good sampling?
Yeah, so we haven't gone through the trouble of modeling the hash function that the switch has precisely. I haven't looked too much into it, but it seems like that's a somewhat guarded secret of what exactly is going on there. And I think people have done it, but it's somewhat tricky. So we haven't really done that. Basically, we just, as I said, sort of do two things. One, the simulator just predicts all of the possible set of outputs instead of just like exactly which one is going to be taken. And then we have basically a statistical test that checks whether the distribution is what you expect. So you send lots of traffic, and there you don't have to use a SMT solver or SAT solver to generate it. It's just like enumerate a bunch of packets and make sure that the hashing works as you expect.
Thanks. Any last questions? No? Let's thank Stefan.
Thank you.